A2 further maths, arc length and surface area. Okay, so what I'd like to do is just have a quick think about this question. You don't need to do anything apart from a bit of thinking. So you can see I've got a function there. It's a function of x cubed minus 4x squared plus 4x. And you can see it's between the limits of 0 and 2. And I'm not looking at an integration question, which will be the area under that graph. What I'm looking for is the length of the actual arc itself. So the length of that curve section. So how would you go about working out the length of that curve section just there, that arc? Right, so have a think about that. Pause if you want more thinking time. Okay, so you'd be right by thinking, let's just do it with straight lines. Okay, if we could think about doing straight lines and connecting up certain points, then we can work out the length of those straight lines, and therefore we can estimate the length of that arc. And that's exactly what I'd like you to do, please. Using 4 straight lines, can you get an estimation of that arc? Okay, so just pause there, see if you could do that yourself using 4 straight lines. Okay, so let's see if you did the same 4 straight lines as me. Now the reason why I picked 4 straight lines is because I can equally space out between 0 and a half and 1 and so on. So I can space out my straight lines like that. Now you can see that it's not exactly the same length, but it's a good approximation. All I need to do now is figure out the length of those straight lines. And so you might be thinking, well, why use a straight line? Because you can easily work out the length of this straight line using Pythagoras' theorem. So hopefully you can work out the length of each of those lines using Pythagoras' theorem. Now again, I'll pause and give you an opportunity to work out that length yourself. So just pause there. See if you can calculate the length of those 3 sections. Okay, so what I would have expected you to do is take each of these values, substitute it into there to give you a height of how high you go up, and therefore you'd have a height and you'd have a length across, and you could work out the hypotenuse. So what I end up with, I'll do a bit of maths for you if you didn't do it yourself, is the hypotenuse there, length of the hypotenuse of the second one, and the third one, and the 4th line. Now once you've got those 4 lines, you can calculate that length, and hopefully you've got an answer of approximately 3.17. So that length, that arc, is approximately 3.17 units long. Okay, but not perfect, of course. So the question I would ask is, how could you actually improve that approximation? So what could you do to potentially make that approximation even better? Okay, so I would have expected you to say something along the lines of increasing the number of straight lines. If you could increase the number of straight lines, for example, if I increase them to 0.5, you can see that the approximation is much better, even with just doubling the amount of straight lines. So the more straight lines you could do, the better your approximation will be. Okay, so what could I do to improve it further? I could increase those number of straight lines. Now I could write this, rather than writing S1 plus S2, I can see it is just a summation. So therefore I could write it using summation notation. I could write it like that. It's the sum of all the straight lines from 1 through to 8. And of course, my approximation could be improved by increasing that number there by as many as I need. So in this case, I've got 8 of them, but of course, if I increase it to about 100, then I'll have a very good approximation for that length of the arc. Okay, right, so let's just take this for a minute and let's just concentrate on this SI bit. How did I get the length of one of these lines? Now you know that I got the length of one of those lines by using Pythagoras' theorem. Okay, so there's my line and there's my 2 lengths. Now if people haven't seen this notation before, what that triangle means is a change. It means a change. Some of you might have seen it in science, you might have seen it in GCSE science, you might have seen it in some of your maths books. So that triangle means a change in the x value. That means a change in the y. And when we write dy over dx, that's what we're talking about, a change in the y and a change in the x. Okay, right, so that's what I've got. Now how could I work out S then, the arc length, this approximation of the arc length? Well, I could write it using Pythagoras' theorem. It's the change in the x value squared plus a change in the y value squared, all square rooted. So I could write that. Instead of writing si, I could write it as a change in x and change in y 1. That would be s1. S2 would be a change in S2, change in Y2, and so on. So really, all I'm doing is substituting that I in for different values. So I've come down to this formula here. So this formula here, I could change that n value. I could work out the length of each of the lines, and that would give me a very good approximation for the arc. Okay, it won't give me a perfect answer, but it'd be a good approximation. And the higher your n value, the better that approximation will be. Now, of course, the issue is doing Pythagoras 4 times was bad enough, but you imagine trying to do it 100 times to get a really good approximation. There's got to be a better way. So what we're going to do is we're just going to play with this formula for minutes, this one on this side, which is the summation of all the straight lines. Now, what I'm going to do is I'm just going to rearrange it slightly. And the first thing I'm going to do, just check you're happy with this, I'm factorising out the delta xi squared. So I'm factoring out that. I know it's not got a factor in there, but what I can do is I can do a little bit of rearranging, as you can see there. I know that that multiplied by that, these two delta x squareds will cancel out, leaving me the delta yi. So just check that you can see that that times that is that, and that times that is that. All right, it's just written in a different format there. Now the reason why I've done that is because I can actually square root this part just here. All right, I can square out this sigma x, and you'll see why in a second. So all I've done there, that's still the same answer. That still works out the length of each of the straight lines. But what's important about it is I've got this delta x at the end. Now I know, because I've seen this before with all the sum of limits, is that the closer and closer, or sorry, the smaller and smaller the delta x, the change in the x value becomes, the bigger and bigger the number of straight lines you're trying, what's going to happen to this summation notation, it's going to tend towards a limit. If it tends towards a limit, that's when I can replace it for an integration. As the n gets closer and closer to infinity, in other words, I have an infinite amount of straight lines, this delta x is going to start to approach 0. Okay, it's the limit of the x values. So how do I write that then? I can write it like this. The limit of the x values, the limit of the y values, both of those will start tending towards, certainly the delta x will start tending towards 0. They'll get very, very small. This bit gets replaced for the integration, because that is just a summation up to the limit. So therefore I get this formula just here. And this is the formula for the length of an arc. Right, can you grab your notebooks then? Let's just put that down in our notebooks. It's nice to see how it's formulated, but you don't need to be able to do that yourself. You might have a situation where they give you a proof on it and you have to do some spotting, but realistically, it's more likely they're just going to expect you to be able to use a formula. So let's make sure we've got this nice and clear in our notebooks then. So there's my general arc. So just go a quick sketch for your notebooks. General arc. You've got two limits, and what we're looking for is the length of this section between A and B. We're looking for the length of that arc. And the length of the arc between x equals A and x equals B, you can use this formula just here. And this is the Cartesian form. We're going to look at the parametric form later on. So this is the Cartesian form. For example, if you had something like y equals x squared plus 3. If you had a Cartesian equation, you would use this Cartesian formula just here. Okay, so pause there so you can get down what you need in your notebooks. Okay, so let's go back to that example that we started with, and let's get the exact length of this arc S. So I want the exact length of S. So instead of doing it with straight lines, I'm going to use the arc length formula. So I can see that this bit just here is the differentiation of this function just here. So I differentiate this function, substitute in there, I square that answer, I do 1 minus whatever that value is, and then I square root it. And then I can find the integration between 0 and 2. So what I'm going to do is I'm going to differentiate that, and I can do that. It's going to be 3x squared minus 8x plus 4, substitute it in there. I can square it, okay, so I could do that, and I can add 1. But to save you a bit of legwork, what I'd like you to do is use your calculator. So grab your calculators, make sure you know how to do this. The examiner expects you to be able to use it at times. So use your calculator and just try typing that into your calculator rather than worrying about doing it. All right, because it's a bit of a messy integral. Okay, so pause, give yourself a chance to write it properly in your calculators. Okay, so you know if you're roughly right, because you can see it's not too far off our approximation. The answer is 3.26 units long. Okay, so instead of actually using those as straight lines, you now have a formula for working out the arc length. Okay, so grab your notebooks. We're going to have a look at a question on it. And as you can see, it's not so much the equation that's difficult to remember, although you get given that in your formula book. It's not the equation that's so difficult to use, it's the actual integral itself that usually causes the problem. So what we're going to do is we're going to do this. It's 2 parts. Show that s equals this, and then hence find the value in the form blah 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 blah. Okay, so give you a chance to write it down in your notebooks. Pause there before we go through the answer. But what I'd say is have a quick go yourselves at just even if it's one little bit of it. Okay, so let's have a quick look through the answer then. Hopefully you had a bit of a go yourself and see how far you got. So what I certainly would do is just make a note. I know I'm going to use the arc length formula. I can see that the arc has the equation to find, hence its length is s. I can see it's talking about lengths of arcs. So therefore I can grab my formula book and I write down the formula straight away. I also notice it's a Cartesian equation. I said you'll see some parametric equations in a minute. So therefore I pick the Cartesian formula from the formula book. Right, now the first thing I want to do then is work out this dy over dx. I need to work out dy over dx because then I can find this bit under the square root. So dy over dx, I take that function just there and I'm going to differentiate it. You could differentiate it using a bit of chain rule in there. Don't forget there's extra minuses, but it's a minus x squared, so it's going to go to plus 2x. So I could differentiate it and get that function just there. Clearly the 4 disappears, the minus x squared there goes to minus, hence 2x, and the ln is 1 over, so that's where this function comes from. And you can clearly see that the bottom differentiates to the top, hence back to ln. Okay, so we've got dy over dx. We can certainly square that. All right, it's going to get us 4x squared over 1 minus x squared all squared. And then I could do 1 plus it. So I can write this bit out. I can certainly work that part out, substitute it in, and let's just neaten this up. Let's put it as a single fraction, see what I get. So I've got common denominator there, 1 minus x squared squared over 1 minus x squared all squared. Then I can add it to that, which is what that bit is. Okay, so just check you're happy. What I could do now though, is because I've got a common denominator at the bottom, I could certainly add the tops together. So I could do that. And there we go. I can see that I've got those 2 parts. Okay, so we can neaten up that numerator a little bit. And if we neaten up that numerator, it's going to go to 1 plus x squared all squared. And that's not really a surprise because, as you can see up here, we're getting close to the answer they want. So what's the difference? Well, this is the 1 plus dy over dx all squared, which is there. This is the answer, so I need to square root it. So we can see that once I do this part, if I square root that, I'm going to get the answer that is required. So I've done the show that part and I've got down to this formula just here that's going to work out my arc length. What I need to do now is I need to use integration to work that out. I'm not saying you can't use your calculator, but it's unlikely your calculator will keep it in exact form. Okay, so the examiner is expecting you to certainly show how you would get the answer from that. And the examiners know you've got these calculators, so they will give you questions that force you to show your integration skills. So I could be able to leave you at this point and say, right, can you work out the integration of that? All right, so you definitely need to pause. You definitely need to think about how you'd integrate that function yourself. There's a couple of options. Okay, so let's see if you did either of these options, or maybe a different option. I'm looking at the bottom, the denominator, and I can see it is a difference of 2 squareds. So what I'm going to do is I'm going to change it to 1 plus x and 1 minus x. So using my partial fractions, I can see I can change it to 1 plus x, 1 minus x. I've noticed that the order is the same on the numerator and denominator, hence I have the value there, the a value, and then these parts can be separated out with b and c because they are only 1 order less than the bottom. So there we go. I've sorted out a partial fraction. Yes, I know that's minus 1. I can see that straight away. And I'm going to just give you these two answers because I'm sure you've got the skills to work those two out. So there's a way of doing it. So a equals minus 1, b is going to equal 1, and c is going to equal 1. So there we go. That is an alternative way of writing that bit just there. So what I can do now is I can replace that part for this. Okay, some of you might have done an alternative method. Just to show you that, I can see that I could write this in this sort of way. Okay, so I can see that the top can be separated out. So some of you might have chosen to do it like that. And if you do it like that, you could dive straight in and use your standard integral for that bit. And of course, that bit will just be 1. So that's an alternative option of using the standard integrals from your formula book. Most of you are probably more likely to use the partial fractions though. So there we go. Let's just see where that other answer came from. So I've used my partial fractions, I've separated it out, and now I can just go through and work out the integral of each of these bits separately. It's not as bad as it looks now because I can see that that just differentiates the top. That differentiates the minus top, so I can do that as minus minus 1. So therefore, I end up with this answer between these two limits. What can I do now? It's just a case of subbing these two numbers in and neatening it up. So let's see. I substitute in my 3/4, I substitute in my 0. Ln 1's quite nice, of course, they cancel out. So I end up with minus 3/4, Ln 7 minus Ln 4, minus Ln 1 minus Ln 4, and of course all this side here was equal to 0. So these two can cancel out, the two Ln 4's, and so what am I left with? Ln 7 minus Ln 1, which of course is 0. So I end up with my answer of Ln 7 minus 3/4. The p-value is definitely one of the integer values, so that's fine, and that is definitely a quotient. So I can see that as a 3/4. Very well done. A lot of maths in there, a big question, be a big mark question in that exam. Okay, so well done if you powered through that. Okay, so I've mentioned Cartesian form for the equation. Let's just have a quick look at the parametric form for this equation as well. So with parametric, of course, that's when you've got two functions, in this case x and y, that are separated by another variable or a parameter, in this case t. Now if I've got this formula just here, and instead of y and x, a Cartesian equation, I want things like dx over dt and dy over dt, because I've got functions in terms of x and t. So what I'm going to do is I'm going to do a bit of chain rule in this to give me an opportunity to bring in dt. Now I can do that by writing something like this equation in terms of dy over dt, dt over dx. Okay, so I can change it into a different format. I can also change the dx part by using the chain rule there as well. That dx is the same as dx over dt, dt. These two are cancelled out, leaving you the dx. So I can do that. Okay. Right, why does that help me? Because I can bring that inside the function the same way as I took it out before. So I can bring that inside the function and make it squared. And once I'm in this stage, I can then put it back into here. So what's going to happen? I've got that multiplied by that part, which is going to get me the dx over dt all squared. And that multiplied by that is going to get me dx over dt squared, dy over dx squared, which means I can put them together. The dx's cancel out, leaving me that formula just there. There's a couple of ways you could have shown that, but it's quite neat to see how you can get from the Cartesian to the parametric. It's more likely you might have a situation like that in your exam because it's quite a nice, easy few steps that you might end up having to do some sort of problem solving or some sort of rearrangement. It's more likely though that you just be expected to use these two formulas. Okay, so pause if you need some more time. Okay, so just in your notebooks, you've got the Cartesian formula from before, so you don't need to copy that bit back down, but you can also add to that by putting the parametric equation. So the parametric equation looks like that, very similar, but as you can see, it's in terms of t at the end. So you're integrating in terms of t, and you've got your dx over dt and your dy over t as separate parts. Both of those formulas are given to you in your formula book, so you don't need to learn them, but you do need to know how to use them. Okay, so pause to give yourself enough time for your notebook. Okay, so let's have a quick look then I'll let you have a go at some questions. I'm going to got the parametric equations. X equals r sine theta and y equals r cos theta, where r is just some sort of constant. It's the radius of the circle, and the theta value is a variable that's going to change. As the angle changes, you're going to plot this. Now, you guys hopefully recognize that as a circle equation, okay? Because if you did something like x squared plus y squared, you will see that that gets you the same formula. But just try that yourselves, x squared plus y squared, and see what you end up with. Okay, so you can see that it's going to be a circle formula. So seeing as this formula works out the arc length, if I work out the formula of the arc over 2 pi, I would hope I would get the circumference of the circle, the total arc length of a circle. So that's what I'm going to try. I'm going to show the formula gets you 2 pi r, which you obviously learned from GCSE. So there's my two formulas, and I've differentiated them. So I can see that dx over dt equals r cos theta, and dy over dt equals minus r sine theta. Okay, so there's my arc length formula straight from the formula book. If I substitute those two values in, so I'm going to get that answer. So r cos theta squared minus r sine theta all squared. I can expand those out. I can factorize the r, so I get that. And lo and behold, I get cos squared plus sine squared, which of course you know that cos squared plus sine squared equals 1. So that's going to just go to 1, leaving me just r. So I'm integrating just the value r in terms of theta between 0 and 2 pi. So that's going to be r theta. I hope none of you are thinking it is r squared over 2. Remember, you're looking at just a constant value, a constant r value in terms of theta. So the answer is going to be r theta, which is quite interesting because that's your arc length. There's your arc length formula right there. So I'm looking at the arc length between 0 and 2 pi. So what do I end up with? 2 pi r, exactly what you expected. The arc length of a full circle, of course, is a circumference 2 pi r. All right, so it's quite nice seeing the arc length formula proving a result that you've known for a long time that was just given to you. Okay, so what I'd like you to do is spend some time on exercise 9F on page 222. Right, so what we're going to do is we're going to look at the surface area of revolution. Now, you've done volumes of revolution, but what we're going to look at is a surface area of revolution. Now, that fits nicely with the work you've just been doing, because when you did the volumes of revolution, you looked at working out the integration, which is the area underneath the curve, and you span it to form a volume. Whereas a surface area is taking an arc length, which you've just done, and spinning that through 360, which will form a surface rather than a volume. You imagine spinning a straight line around 360, it will form a surface rather than a volume. So the formulas are going to be quite similar to the ones you've just seen. Right, there's a lot of things that are in there that link the surface area, but also link the volumes of revolution that you've seen before. Okay, so let's just have a look where these come from. You can see that it's 2 pi because you are looking at rotating it round 360 degrees, which is where the 2 pi comes from. You're doing it around the x-axis, which is why it's dx, and the y value comes in there because it's the how far away it is from the x line at any given point. Okay, so we've got that sort of formula, very similar to the formulas that you've seen before when it came to volumes of revolution. You can also do it in parametric form as well. So you've got that formula, and you can see the only difference there is you've got dt at the end, and you've got this slightly different change here because it's to do with parametric equations. Okay, right, but this is rotating around the x-axis, hence why it's the surface area around the x-axis as opposed to arc lengths. Okay, so you've got both of those formulas in your formula book. You don't need to learn them. If you want to see the full proof of them, then you can certainly have a look on Google, but it is beyond your spec. All right, you can do it out of just a bit of fun, but you're more than welcome to have a look at those and ask me any questions if you get stuck with it. Okay, as I said, both on the formula book, so I pause there if you need more time. Okay, so just grabbing your notebooks then. We'll go look at one more exam question on this, and then I'll let you have a go at some work. So a curve C is given parametrically using those two functions. So I've got two hyperbolic functions just there, and I'm looking for some keywords. I can see it's talking about rotated through 2 pi radians, about the x-axis. So at this stage, it could be, for you guys, it could be a volume of revolution question, like you did in the first year, or it could be a surface area question from your second year. So always look for some other keywords in there. The exact value of the arc of C, so there's the hint. You are looking at the arc length rotated through 2 pi radians, okay, as opposed to a volume. There's no mention of the word volume in here, so it's not a volumes of revolution question. So I'm going to pause, give you an opportunity to make sure you've got the question written down neatly in your notebook. You can feel free to have a go. I'd expect you to have a go at some of it yourself, okay, and then replay when you're ready. Okay, so the first thing hopefully you did is you started either writing down the formula, all right, straight from the formula book, and then once you've done that, you can work out dx over dt and dy over dt, because you're going to need both parts of those. So you may as well pick up some easy marks in that exam. So if I look at differentiating these, it is going to be simple chain rule in this case, and I know that cosh goes to shine and shine goes to cosh. I know that the 2 can come to the front, hence it'll cancel over that half, and this one's going to just be 2 as well. So what do I end up with? I end up with shine 2t there, and for this one differentiated, I'm just going to get 2 cosh t. So there we go, I've sorted both of those out. What I can do now is I can square them and add them together. So I'm going to get shine squared 2t plus 4 cosh squared t. Right, so I've simplified those. I might want to play with them a bit more. So I can more than happy just to have a play with those a bit more. And what I'm going to do is just change this bit here to single angles rather than a double angle there. And then hopefully I can maybe do something with this bit to neaten it up. Now I can clearly see that I've got a 4 cosh squared t common in both. So therefore I can pull out that 4 cosh squared t, and I end up with this shine squared plus 1. So shine squared t plus 1, which is, of course is cosh squared. So that whole thing simplifies down to 4 cosh t to the power 4. And it's more likely in your exam, the examiner would have given you that as a goal to work towards to start with before asking you the second question. Okay, so don't panic too much thinking that seems like a lot of work, or how did you know to go that far? You're more likely to get told that in your exam. Okay, so feel free to make a note next to that if you want to. This would be a part A section to the question. Okay, so I've got those bits worked out. So what I can do now is I can go back to the formula. So the formula states that to work out the surface of revolution, I've got 2 pi, lots of the integral of y, square root of this, dt. Okay, so I can do that. I can also start filling in some of the parts. I've clearly got this bit that I can fill in there, and I'm going to square root it, so that's going to neaten that up. I can also put in the y value, which was 2 sine t. So I can substitute that in there, and I may be able to take some numbers out, or I might want to just leave it. So there we go. I've substituted in my y value. I've substituted in my d squared, dy over dt squared plus dy over dt squared, sorry, dx, is that wrong? And then, once I've got to that part, I can see that I've got 4 cos t to the power 4. Okay, this can clearly be square rooted, so that's going to be 2 cos squared t. So we end up with this answer just here. Okay, I can maybe pull that 2 out. Okay, and maybe have yet another 2 on the front, so I've got 8 pi in the end. So I pulled the 2 out twice, okay, from earlier on, and I'm left with this integral just here. Now you've seen these types of integrals coming up a few other places. Hopefully by now you're getting so used to seeing these integrals, you're thinking, right, it's going to be substitution. And what's nice about this is if I make cos t equal to, let's say, u, the integrals, the differentiation of that's going to be sine, and it's going to cancel with this part just here. All right, so we can see that happening. So let's take that integral. I'm going to let u equal cos t, so therefore dt ends up being 1 over sine t du. All right, just make sure you're completely happy with that. I differentiate that to get du over dt. A bit of rearranging goes to this, because of course the differentiation of cos is sine. Right, why does that help me? Well, that can go in there. That sine will cancel with that sine. And that cos t, as I can see here, is going to go to u squared. So you can see that that's going to cancel with that. That's my u squared. So therefore I get down to this. What's absolutely vital with this though is noticing that your limits are to do with t. At this stage, I like to just either keep a note that it's t equaling these values. Some people just take these out completely and bring them back in later on. Other people change it to the u value, and you can certainly do that. So you've got cos 3 on the top and cos 0 on the bottom, because it's to do with u. What's absolutely vital though is you don't leave it as 3 and 0, because that would be technically wrong, because this is to do with u and that's to do with t. So be careful. Careful with your limits. Okay, but I could do this, can't I? Because this is just going to go u cubed over 3 between these two values. Now at this stage, you can either change your limits and substitute them in, or you can put your u value back to t and then you can substitute 3 and 0. It's totally your choice. Okay, totally your choice. You're going to get the same answer either way. So I've converted back to t, and now I can put in my 3 and 0. So I end up with those two answers just there. Okay, and you can see you would have got the same if you had substituted in your cos 3 and your cos 0 in for u. Okay, so well done for getting down to that answer. That's what you should have got. We can still neaten it up, of course, because we know that cos 0 is just going to be 1, and we've got cos cubed as this part just here. So we're not quite finished. And again, in that exam, you'll be getting some hint that your final answer wants to be in a certain form. So at this stage, if you got down to this answer, great. If you got down to this answer, great. I'd just like you to pause, have a play with this yourselves, see why I've bothered changing it to this form. Can you neaten this up at all? Okay, so pause if you need to. And well done if you managed just to neaten it up to that. Okay, so what I'd like to do is just have a quick go at this exercise 9G on page 225.